Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VJEC Institute of Engineering Technology. As a part of Dynamics of Machinery course, we are discussing mechanical vibrations, various types, applications. Now today we are going to see effect of inertia due to mass of the spring in free undamped vibrations. We have seen so far what are vibrations and the model of vibration, spring, mass, the object must have some elastic property and mass. So we have seen the various terminology involved in that also, and how vibrations are classified depends on various criteria we have seen so far. Then we have seen important this type of motion involved in the vibration of any object is generally simple harmonic motion. The equation which we have framed when we will take we have taken mass attached to the spring, and this mass is given some displacement. Then we have seen the inertia forces on the spring is mx double dot, and the restoring force which is reaction on the mass due to spring is kx, we have seen. So ultimately we could be able to write the expression for the equation for this is mx double dot plus kx equal to 0. This is as per D'Alembert principle or Newton's law of motion. So in this we have seen already the mass attached only we have taken under consideration, but the spring has also having some mass. We have not taken the mass of the spring effect okay, due to this inertia forces before. Now we are going to see what is the effect of this mass in the final relation. Final relation we have seen natural frequency is under square root k by m, okay, or it is g by delta, we have seen already. So we will see today how the mass of the spring is going to be affected. The solution of this general equation is in the form, as we know that x the amplitude is a cos omega nt plus b sin omega nt. We have seen different forms also in the previous lectures. So now we let us take the mass of the spring, effect of the mass of the spring. Let us say m dash is the mass of spring wire per unit length. So this is the spring wire. Okay, mass of the spring per wire. I am not attaching any mass, but we will consider mass of the spring per unit length is m dash. Then v is the velocity of free end of the spring at the instant under. If you just displace then with x, then let us say v is the velocity of free end of the spring at the instant under consideration. L is total length of the spring. Total length of the spring is L. Let us say L. Okay. So this is the L. Then small element let us take. Okay. I will draw here small element of the spring. Let us take small element dy distance from dy thickness. Let us say length. We can say from y distance from. Okay. This is y distance from this end. Then total length is L, you know, y becomes 0 to L. So dy distance we have taken. So dy element we have taken, and okay, other end is fixed and one end is free, you know that. Then K of this element, this small element dy length element, kinetic energy of the this element, if you want to write, you can write of m dash. M dash is mass per unit length and delta y is the length, that is dy I said, okay, length of the spring. Then this is mass and v square. Okay, velocity at the end is v, but it is at y distance. So we can write per v velocity for entire length, that is L length, but what is the y length, because for this element we are talking about y length, what is the velocity, then we can write y by L into v, okay, v mv square. This is the mass quantity, this is velocity quantity at on that element at a distance of y. So you are able to understand this is the kinetic energy for this element. Then entire spring we want, then for entire spring kinetic energy you need to integrate 0 to L this, because delta y thickness it is, y is the variable, delta y differential variable. Then you can have kinetic energy of the spring by integrating this 0 to L, you will get kinetic energy of the spring due to its own mass. I have not attached any mass. I have taken m dash is the mass of spring per unit length. Then if you do that process, you will have integrate, okay, integral 0 to L m dash delta y, this is half, okay, and y by L v whole square. This is kinetic energy integration. Then you can take these terms m dash, okay, half m dash, and this is v square, okay, by L square, and you will have y square delta y. Okay, so I think you are able to understand. Then these are the variables must shown in integral, because v is the velocity end of the spring by applying some displacement, then L is the length of the spring, all this. Then you will have this, do the integration, you will have half m dash v square by L square, okay, and it is y cube by 3 over limits 0 to L. Okay, so if you substitute this, you are going to get half 1/3 and half m dash, okay, L square and v square is there, and L square and L cube L, okay, you are going to get this L square and L cube, if you cancel, L is remaining. So yeah, 1/3 of m dash L is mass of the spring, you can write mass of the spring, mass, and velocity square, velocity v at the end of the spring. So this indicates half mv square is, okay, half mv square is, okay, kinetic energy. 1/3 of that kinetic energy, if you attach the some mass, suppose this is half mv square, 1/3 of that kinetic energy is going to, you have the as a contribution of spring. So you can see this, it is 1/3 times kinetic energy of mass equal to that of the spring moving with the same velocity as the free end. Okay, this shows that the inertia effect of the spring is equal to that of the mass, 1/3 of the mass of the spring concentrated at the free end. You have seen this relation, 1/3, okay, times kinetic energy, whatever mass spring has, m dash. So 1/3 of part of contribution towards kinetic energy due to consideration of mass of the spring. Okay, then equivalent mass at the free end, if you attach m is the mass, suppose, then equivalent mass you need to consider m dash is mass per unit length, we said, okay, m is mass of the mass attached, then equivalent mass is, I will say m dash L is equal to m1, okay, m dash L by 3. This is the equivalent mass you need to consider attached at the end of the spring. Okay, mass is mass attached, then m dash L by 3 is 1/3 of the mass of the spring you need to consider at the free end of the spring as a mass included along with the mass attached. Okay, so this is the effect, effect of this is mass of the spring by 1/3 of the mass of the spring. In the same way, in the relations you need to use this. Then we know that, okay, we have written frequency equation. Okay, what is that frequency equation we have written here? Fn, okay, cycles per second, that is edge, 1 by 2 pi into 1 by 2 pi into square root k by m replaces with m plus m1, mass of the spring, 1/3 of mass of spring. This you need to take care. It can be noted that the net force on the spring at any instant tending to restore the vibrating mass to equilibrium position is, what is the restoring force? Is kx, spring stiffness k, so kx, which is proportional to the displacement of the mass. You have seen. Okay, so then this is true for any vibration due to elastic forces. Okay, so while considering mass, suppose this equation you want to write m plus m1 mass of the spring 1 by 3 into x double plus kx is the 0. This is the relation if you want to write differential equation. So similarly, if you write frequency, this is the same way. Thus, in a vibrating system in which the restoring force is proportional to the displacement from the equilibrium position, the frequency of system always given by Fn equal to 1 by 2 pi under square root over square root k by m. M here is, if you consider mass of the spring also, then you have to add. Also we have seen it is 1 by 2 pi root square root frequency is g by delta. G by 1 by 2 pi g by delta. Why I am talking about this delta term? This is a static deflection under consideration of suspending mass. For example, if we take consider rod, some rod having mass, rod of length L suspended from one end, then a mass m is suspended at the free end. Mass m is attached to the rod. Then the static deflection, you know that delta is m. Static deflection delta you can write weight is mg into L by AE. And you are familiar with this equation. Delta is equal to PL by AE or WL by AE. That is mg here. M is mass attached, ML by AE. If you won't consider the mass of the rod. So then here A is cross-sectional area, no, E is Young's modulus and L is the length of the rod. You know very well, familiar with all these terms. Now then we can write frequency is 1 by 2 pi under square root of g by delta. G by delta is here mgl by AE. Here you can write AE in the numerator. Then you can see that you will have overall this equation is square root of g will cancel out AE by ml. Right? So if the mass of the suspended rod is also considered, then you can add 1/3 of that mass of the rod. So that you can write Fn equal to 1 by 2 pi square root of AE, m replaced with m plus mass of the rod, 1/3 of the mass of the rod, into L, length of the rod. This is under square root. This is the equation. So overall, the effect of any ear rod or there in the spring, whatever mass of that element which is actual mass is attached, you need to consider effect of that mass in the inertia is 1/3 of that mass, and actual mass is attached m. M plus 1/3 of that mass in all the relations. This is very, very important. If the effect of vibrations are much more, then you need to consider mass of the spring or the rod which actual mass is attached. This is very, very important. To accurately, precisely, you need to determine frequency or time period, or natural frequency. So this is the case where we have discussed the effect of mass of the spring on undamped free vibrations. Similar way you can use same thing in other cases also. We will discuss a little bit more about damped free vibrations in our next session. With this, I am concluding this session. We will meet again in the next session. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.